Welcome to .NET for large code bases. We have a lot to go through, so I'm just going to start. So normally, when we look at performance, it only matters up until a client complains. It's not considered through development or anything like that. As soon as it becomes an issue, then you'll probably hear about it. So at some point, performance has affected us. You might have called a call center to update some details, and the lady tells you, can you please wait on the line while the system is loading, just to update your new residency address. Or the client calls you and say, the system is slow, it's hanging, it crashed again, and just for you to see that the server is on 100% memory usage. So at the end, performance creates better software. So think about it as another layer of polish that you add on top of your code. You've maintained it, you have good patterns and everything, but on top of that, you just make sure that every performance is pushed through. Better quality is happy users, that's obvious. As long as the users are happy, then you probably will still have a work to do. So when and how do we measure performance? So normally, again, as soon as it hits production and something hits the fan, then everyone runs around and tries to fix it. So it's ideally it should be done during the application's performance. With that in mind, is you need to understand as well what do you want to measure and how you want to measure it, and what's the goal at the end. What performance does your code need to reach, if I can say it like that. A performance goal is we're only allowed 20% overhead on specific call times, or only certain amount of actions that we do can exceed 1 second, let's say. We use a scientific method to measure our performance issues, and we use tools to benchmark those changes, and then on top of that, the method guides us for our changes. So the scientific method is the general one, but there's a small tweak for performance. We first need to get a baseline, so we profile. So once we know that this method or this code is taking forever, we ask a question and ask ourselves, why is this specific code slow? Then you form a hypothesis, basically. You say, if I can reduce the amount of allocations that this method generates, or if I can minimize round trips to the database, I can improve it. And then make a prediction. If I can improve this, it should get faster. You experiment and analyze then. So by that I mean you break stuff, you make it faster, and you repeat this iteration over and over until you are either happy with the result and you either accept or reject it. So before we start, let's go over a few tools we personally use on our team. And the first one is the Visual Studio Profiler. This is the most basic one. If you're a .NET developer, you'll most likely work in Visual Studio, and it has a very good performance and memory profiler associated to it. We mostly use it for allocations. It's very nice to quickly benchmark a piece of code to see how much garbage you are generating at that point in time. So in this view, we can see that our topmost method and the amount of garbage or allocations that it's generating. But we'll get to allocations in a bit. The second tool that we use is the Redgate Profiler. It's also a memory and a performance profiler. We use it mostly for memory leaks. And it's the Visual Studio one has this feature as well, but we've just come accustomed to using the Redgate one. So the idea is you want to benchmark a certain piece. You perform an iteration to warm up, to basically say you should have everything, and everything that you have should be there. Then you take a snapshot. Then after that, you do a few iterations, and you take a second snapshot. And then in between those two snapshots, you would expect, if you write a desktop app or anything like that, you would expect that you shouldn't have any screens left. If the instances grow, you probably have a memory leak on your hand. So we use Redgate for memory profiling. So a retention graph, when you drill down into Redgate, you can see what is actually keeping the object indirectly alive, or what's referencing it to the nearest GC root. So in this case, we can see that our user window is referenced way back to an event handler. And you can drill down into this as well. In this dependency graph, you can see that way at the top, we have a session class, which has a logout completed event. And there is a event handler collection, which basically houses our target object, the object that's subscribed to this event handler. Next up, we'll get to that, but next up, IR Spy is a free reflector that we use as well. So the main reasoning behind the reflector that we use is for us to inspect our code that the compiler generates underneath, and to see if we have performance issues with any third-party applications, we can use this to see what they are doing under the hood if the code is not obfuscated. But again, mostly use this for our own purpose. So you can inspect the C# code that will be generated, but the most important bit is the IL that gets spit out. You'll gather a lot by just looking at the IL to what the code is actually doing underneath. And then lastly, we use BenchmarkDotNet. This is a NuGet package that is written by one of the CLR teams, or one of the guys that works on the .NET CLR. It's a tool that's very handy where you quickly want to compare something, you quickly want to test something, so you decorate a method with a benchmark attribute, and it performs many, many, many iterations over it, and you can get a clear understanding what's the speed, and then you can also get an indication what the garbage collector is doing underneath. So before I start, performance in our applications is really important, because performance is important for our client. Speed and availability. So responses need to come back within milliseconds, and availability is that the servers are always available. They guarantee a 99% uptime for their clients, so any memory leaks or any server spikes will have an effect on those goals that we have in mind. And then our UI application runs on a terminal server or a VM. So normally memory and CPU resources are very scarce. So again, most of our applications need to be reliable, and our UI runs in a very starved environment. So some statistics. Our application, this was for a total day, but you can measure it in an 8-hour period. So 18 million requests, 13 million of those were from our UI. So that roughly translates to 620 requests per second to our servers. We have 400,000 unique caches. That's like task type lists, any type of list that we need to have in our UI. Our biggest cache has 60,000 entries, and all caches are available in 12 different languages. So we need to keep those lists and caches within memory for when a request comes in to serve it back. We don't want to go to the database round trip, basically. We just want to serve it back. So before we start off and look at some code and examples, I want to make it clear that the stuff that I'm going to show you is our journey and what we did to improve performance and what worked for us. The point that I'm trying to make here is that you need to look at your own project, you need to identify your own performance goals, and you need to find out what works for you. So these are changes specifically to us, but in general, if you write slow code, it's going to be slow. The point that I'm going to make is that you can look at a piece of code, you can roughly gauge that this might be slow, and you optimize that loop, you get like 50 milliseconds, you feel great. You run a profiler over this, and you discover that your bottleneck actually sits way at the top. And by fixing that bottleneck, you would actually gain a lot more performance speed. So profile before making any changes. The focus here is, for the UI, it's mostly memory, because again, they run on a terminal server. Memory is a scarce resource. But for performance, we'll mostly look at hot paths. That's code that basically hits thousands, hundreds of times over and over and over. So the focus and the optimization are on those paths. So think about an entry point into your server where you hit validation, or you need to validate the input that comes in. Those are hot paths, high hit count methods. So there's a few realizations that we came across. The first one is, it's easy to cause memory leaks in .NET. So a memory leak in .NET is not really the same as the C++, but it's referred to as a memory leak. So that's where you indirectly keep an object alive by it's being referenced by another object that has someone else that references him, and it creates a GC root. That's basically a memory leak, right? You need to understand that when you interact with your classes within your code, that's what the object life cycles of those objects are. If I'm subscribing to this event on this class, what is that scope of that class? Does it go out of scope within this method, or does it live longer? That's the basic realization that we come across. The second one is allocations matter. So in the .NET world, we'll get to that, but in the .NET world, you have the GC basically takes away the responsibility for you to allocate memory. So anything you do, there's a portion of memory that will get allocated to it. That part is very fast and is the least expensive. The problem is the cleanup afterwards, because GC needs to track every object that you create to see if it's being referenced by a other object. So it needs to traverse basically all of the objects, and that part is expensive, but we'll get to that. Number 3 is optimize the obvious, then start thinking out of box. So with that is, don't optimize a loop where you can minimize a round trip to a database, for example. You'll get a lot more gains in speed by not going over the network to your database, pulling a big SQL query out and pushing it through. So caching would be a lot better in this case. Again, optimize the obvious. Number 4 is gains. So after you did the obvious now, and you still want to squeeze out more performance, gains are made with small optimizations that are very targeted. So thinking about the code path that you have, right? You would look at this, you would benchmark it, and you would start with optimizing certain aspects of it. By making those small changes, you reduce 50 milliseconds here, 20 milliseconds there, but at the end they all add up. With a high hit count, those milliseconds will make a huge amount of gains. That's not to mention the amount of, but we'll get to GC a bit later. I don't want to run over time. Understand your application's performance-sensitive areas. So as a developer, you need to understand where and what code you're working with. If it's on the hot path, you need to treat the code that you write a bit differently to the rest. If you're writing code on a button click, for example, don't worry about performance. If it's just executing something, then fine. We're talking about sensitive areas. So if you make changes there, you need to understand what it's going to affect. If you look at the CLR on GitHub, if you make any change to the GC's actual code, it goes through a 48-hour stress test before any changes are accepted. It just tells you how important that piece of code is when it needs to run on different environments. You should have that same mentality when you look at certain aspects of it. So let's start off first with memory. Allocations and memory leaks will have an impact on your application's performance and availability. So performance, obviously, is how fast it is. Memory affects your availability. So what I mean by that is, if you have a lot of GC collects, your server latency spikes. But not that. If you are leaking memory, at some point in time, that server is going to run out of memory, and it's going to throw an out-of-memory exception. So your availability is reduced because it's not reliable. Next up, so why do allocations affect performance? So the bottom line is GC needs to keep track of everything that you allocate because it's a managed language. So it's literally increasing a pointer for a new allocation. It's the cleanup that's expensive. So looking at the garbage collector in itself, every managed language does have a garbage collector. So it's responsible for allocating and freeing up memory. It has this tug-of-war battle where it wants to give you leeway by giving you as maximum amount of performance by not intrusive or being intrusive on your application. But it has external factors that basically tells it you need to clean up, or it needs to clean up. If you work in a VM environment where memory is scarce, that automatically makes GC a lot more aggressive because there's only so much amount of memory that you have to work with. So it will collect more. It's a generational collector, but we won't get into that. The point is, it's going to need to stop to clean up after you. This is referred to as a GC pause. So a GC pause is where something triggers or exceeds the current segment, and a collection needs to happen to free up some memory. As soon as that happens, GC suspends all of the threads that are currently running. So basically, your app goes into this empty space where GC is busy cleaning it up, and then afterwards, when it's done, it releases all the threads and work continues as is. Those spikes have an enormous impact on performance. Now, the thing that I'm trying to make here is it's not that .NET is slow or anything like that. You just need to be considerate about that it's in the background cleaning up after you. So the Roslyn guys, if you use Visual Studio 2017, there's a Roslyn compiler. You can view it on GitHub. It is written in pure C#, and they optimized it so much that they get near native performance to it with the benefits of a managed language. So a managed language, or .NET in this case, can be really, really, really fast if it wants to be. So we're going to look at a few allocation smells that we have basically not come up with, but there's a ton of videos out there, but these are normally the ones that we look for. So the first one is boxing. So boxing is any operation where you take a value type and you box it to an object to treat it like an object. So it gets boxed from the stack up until the heap. As soon as it gets boxed, GC needs to keep track of it. Next up is structs. Structs are value type as well. If you, for example, you can box a struct by casting it to an object, or you access a struct via its interface implementation. You get a box operation. Those are allocations as well. String manipulation. So in the world of .NET, strings are immutable, and because of that, any changes that you make to a string causes a new allocation, again, which is garbage that GC needs to clean up after you. And then lastly, link. There's nothing wrong with link. There's a ton of examples out there where you can write expressive code that's easy to read. But we've just chosen on hot paths, we avoid it because we do not understand it's not that we don't understand this, we just want to avoid what the link provider does underneath, but we'll get to link. So let's look at some examples. So in this example, we are iterating, and we have a value that we create plus, and then we log that value. There is a very obvious boxing here. I'm assuming most of you can see it. And it's because int is a value type, and we box it because we log it to an object. I've seen this where, for developer, quality of life, you have a log method that just takes an object, right? That can really be expensive if that code runs on a production environment. It can allocate quite a lot of memory. So structs, so they are allocated on the stack because they are value types, unless they are boxed. So they get either boxed by you explicitly making it an object, or you access a type you access something on it via interface implementation, like, for example, IEnumerable, but we'll get to that. And then beware of defensive copies. So defensive copies is where you, again, this is not an issue. It's an issue on a high hit path. There's no allocation with a defensive copy. It's more to do with when you access a struct that's non-read only, the CLR basically protects the struct by giving you a new, not a new instance, but a new copy of that struct. That copy operation is the expensive part. So if you have a very large struct that gets defensively copied on a high hit count path, that time can add up quite big. So in this example, we have a list and an iList. They basically look the same. There's a subtle difference between the two where the one is looping over list and the other one is looping over iList. So this is not a problem, but there are allocations here. As you can see that the iList generates a lot more allocations than a regular list. So why? The simple reason is when you iterate over a list, it returns the actual struct enumerator, where if you access the list via the iList implementation, the get enumerator is accessed via the interface type. And because enumerator here implements IEnumerator, it will get boxed because it returns the interface type. So let's have a look at link. Again, link is not bad. We just avoid it for, we don't want to. Link does weird stuff. If you write this, it might be fine for one where or first.default, but if you write this expressive tree in where you capture outside variables and whatnot, what the compiler needs to do underneath is based up on him. So again, like one of my colleagues said, link is expressive. You basically tell it what you want to do. How you implement that is up to you. So that's the problem with link that we found. Again, this is on high hit paths. So here, we are basically going through a list of strings, and we're looking for anyone that starts with a lower character or contains a lower character, and we count those. There is a huge difference in the amount of garbage that a link statement generates compared to a regular for each. The reasoning, if you look at the Visual Studio profiler and you look at the allocation hot path, you'll note, in this specific example, you'll notice that the any part generates a lot of allocations. And the reasoning behind that is the any, so string implements IEnumerable of char. And for it to be able that any to iterate over those char values of your string, news up this char enumerator every time to iterate over the string. So you'll get this being newed up every time versus if you did it in a for each, you wouldn't have this issue. Another example here, this is not a functional example. This is more to do with subtle differences where the compiler is doing, I can't remember the word, but basically it's doing shorthand stuff for you. So in this case, we're looping, and we're adding I to a string. Notice that we're not doing I to string here. It's because the compiler is compiling not compiling this down. It's actually boxing that int of you to an object, and this causes the string.concat, the plus that you have, to be compiled to a string.concat of object. So again, this is not an issue. It's just for you to understand that something small like that completely changes how the compiler spits it out underneath. So looking at ILSpy really helps a lot to understand what it's doing underneath. So the fix is to I2 string here, and then you get correct overload resolution. Now you get string.concat string. So if you're looking for allocations and you don't understand why something is generating so a lot of allocations of garbage, then just look at the IL that's being generated. Lastly, so string manipulation. Again, I told you that strings are immutable, and any changes to it, so if you do string.trim, or in this case string.split, or you do string plus plus to something else, that creates a new allocation. So if you have this big chunk of string within memory, and you just trim the back or the start, that whole section, or that whole string gets allocated to a new instance. In this example, this is more to do with understand how your code is used and what class is correct or fit for purpose. So in this case, we're again looping, and the one we're doing is string.concat, another one we're doing a string builder, right? Simple as that. And we're looping a number of times over this. This is BenchmarkDotNet, so it can give you quite an easy way to gauge if you want to add in something. We can see that string.concat is actually faster and less allocations up until a certain amount of iterations. Then the string builder just wins with speed and amount of garbage that it generates. So this is more to do with understand the tools that you need to use at certain points when you develop. So let's look at memory leaks. So memory leaks in the .NET world is basically any object you have that's being indirectly referenced by another object. And because if it's associated to a GC root, the garbage collector can't collect it. So GC roots, for example, are static classes. If you have a desktop app, your shell is a GC root. I don't know what else they are, but if you pin something with a GC, that's also a GC root. So in this example, you can see we have a session class, and we have a logout completed event. And within that logout completed event, there's a list for the invocation. So whenever that event gets raised, there's a few callbacks that need to be iterated. That's how you subscribe. And our user window listens to this logout event. So it indirectly added itself to that invocation list to be notified when that event gets raised. So you can see how the GC root paths go down from the GC root up and down to your object. So the most common memory leaks that we found when we did our cleanup on our code and our environments that are static classes. So developers normally create a static class because they quickly want to store a value in there. And because it's a static class, it's a GC root, any reference that they have to another object, if you quickly assign the last control that the user tapped out of, it will indirectly keep that control alive. Event handlers, again, this is more, you need to understand more than anything else to what you are subscribing to. Event handlers are not bad or anything like that, but they cause a lot of memory leaks that we found because developers are just quickly subscribing to events because they want to do something, but they never unsubscribe. And if that object lives long enough, it will indirectly keep that alive. And then closures is the most interesting one, where you basically use a lambda expression where you also want to do something, but there's some trickery that happens underneath in the CLR. And then caches without a discard policy. So this is not a leak as per se, but if you have a list that continuously grows, it's memory wasted. Like if you just keep on adding stuff to that static list, it's just going to keep on growing. So a quick example, static classes. We have the session class, which is static. You might have one similar in your application. In this case, we have a user details object. So after you've logged in, you basically store the current user after you've authenticated within this session. So that user details is being kept alive by the static class. That's a GC root. So the garbage collector can't collect that user details, hence why you made the session class static. Event handlers. So quick example, we have a login button and we have a log off button. we basically authenticate, and once we authenticated, we new up a user window, for example, and then we show that window. And then we log off, that window gets closed, always. So the user window subscribes to the log off event, and when that event fires, it closes itself. Okay. Remember that session is a static class. So looking at the ANS memory profiler, we can see that between snapshot A and B, by iterating this process, we can see that the instances for our user window has grown, obviously. It's because, I've shown this quite well, but again, it's because the user window, by subscribing to the logout event, it added itself into that invocation list. That invocation list is a hard reference to it because it needs to be called back when that event is raised. So it will keep it alive and GC can't collect it. So the fix is, on the logoff event, just unsubscribe from the logoff event. Easy. In this example, let's say we don't want to do that. We create this fancy lambda where we new up our user window, and when that logout event fires, we close the event. We close the window. Right. There's a subtle problem with this as well, because you can see that that method scope, as soon as it goes out, where is it going to live? How is it going to work? So the compiler generates a closure for you underneath. And this is referred to as a display class. We can see in the memory leak that this is indirectly keeping our user window alive. So if we look at the retention graph, we can see again, session is at the top, and we see that our user window is being kept alive by this display class. So looking at ILSpy, we can see there's a delegate. There's nothing too obvious yet. But looking at the IL, you can actually see that how this class is generated. The compiler generates this class for you to capture that user window variable. And then it's underneath hooking up to that logout event. So if we wrote this class in C#, it would look something like this. You have your user window at the top, and the method callback for the logout event that's raised. And the compiler basically does this for you. New up the display class, assign the user window variable to it, and register the logout event. Lambdas are not bad, but you need to consider, again, the lifetime to what you're listening to. If you do a lambda on the control itself, for example, that whole island will get disposed when GC collects it. So that's not an issue. It's more to do when you're subscribing to something that's living longer than you expect. Quickly, caches without a discard policy. If you have a static list and you just keep on adding to it, it will grow over time. GC still needs to keep track of all of these objects, so it will affect its performance underneath. A more better approach is to use the memory cache framework that's in .NET. It's very fast. You can do something where if a cache item is not accessed within a certain amount of minutes, it gets stale and it will automatically get thrown out. So on performance now, we found that 2 points affect performance like raw performance, and that's usage of exceptions for control flow. I'll show you now an example. And then pooling expensive objects that are created. So in this example, we looping, and every fifth one, we just continue. To your right, you can see that we throw an exception just to catch it underneath. So it's subtle, but not a problem. The difference between the performance is huge. Like, you need to understand that when an exception is thrown, there's a lot of stuff at the background that the CLR needs to that it needs to do for you. It needs to ensure the stack trace before it can raise the exception or lift it. So just make sure that, again, if it's on a button click, like an authentication error, that's fine. If you are lazy and something comes in and you just raise an exception just to continue later, then that part will add up. It will get expensive. Quickly touching on pooling. So pooling is a technique where you basically reuse the exact same object every time. So a string builder is excellent for this. A string builder is expensive to new up, but its reusability is nice, because as soon as you news it up, it will allocate a piece of memory on the heap, and will basically reuse that same piece of memory every time that you use it. So this pool, basically, we lend something from the pool, and when we're done with it, we release it, we clear the string builder. Pooling is unique where it can save you memory performance, and that it can increase performance, because you're not generating garbage, and you are not creating an expensive object again. So you're just reusing the same object every time, over and over. So you can see that we lend something to the pool, do something with it, and then release it, just for it to be reused later. Another example of pooling is where you have an object that basically has state that's commonly raised. So in this example, we have a property change, so just say that something specifically has changed, and we want to notify someone about this. So it's a class that just has one read-only property, and we can pool those just to reduce the amount of allocations that we generate, hence helping out the garbage collector, that it doesn't need to clean up afterwards. So to conclude, profiling should be really done during development. So every time that you do a major CR or major Scrum or whatever you want to call it, you need to profile. But you need to have performance goals on that profiling during it, because you want to measure, did it get worse or did it get better? And you want to have performance goals on certain part of your code, not on the whole application, but a performance goal in this case would be, we would try to use a minimum of 500 megabyte during peak working or usage of our application. Then use tools to identify and help investigate and improve performance issues. And then use the scientific method to guide you and help you to make those changes.